welcome for the second day in this nice city in Porto. Thanks for the organizers. I'm listed as one of them, but I didn't really do the job, so Andi and Katrin were actually doing this job. So it's a very nice location, I think, very nice city. Awesome food here, so enjoy your time and now enjoy some code-based crypto. So the lecture that I am giving to you, it consists of two parts. So we have 2 times 90 minutes, so the whole morning for code-based. I hope you are prepared. Okay. And but it came out of a lecture, a crypto analysis lecture that I teach like in 5th semester. So it's really supposed to be basic stuff. I'm doing a little bit fast forward because we have only 2 lectures now instead of 14. So I kind of skip over most of the crypto analysis part. So part 2 is it's mostly based on crypto analysis. But what we want to really understand today is a very old, almost historic crypto system that's called the McAleese crypto system. So you might know RSA was invented in 76 and published in 77. So it's kind of the second public key encryption system and McAleese. And we had it so for a long time. But it was kind of ignored in crypto, and I will show you already on the first slide why it was ignored, and we had RSA, and we had discrete log, and we were happy in having that. But now that we have quantum computers, it's kind of reinvented, and we think of it anew, and it was also kind of the favorite schemes in the NIST competition. And I think it's close to standardization. The only issue with classic McAleese is that it has huge public keys. And you will get an idea in this talk why it has to have these large public keys. It's kind of inherent for this, right? And that's why kind of ladder schemes were the winner. Also, code-based schemes are also very attractive for crypto because they live in F2. Yeah? So what you see here, the matrix G, that's a public key. G is for a reason, we will see in a minute. It's a generator matrix of some vector space. And here already is a dimension of some public key in McAleese. And this is actually from this classic McAleese, which is maybe going to be the standard. It's the smallest instance, so it's a 128-bit security instance, right? So you have 2,720 rows and 3,488 columns. That's a lot. So if you compute these are bits. So there are 1 entries, and this is already about 9 megabyte. So in security, it's comparable with RSA 4096, which is of course 4096 bits actually, right? So that's huge actually. But people still like it, right? So it's F2, so it's really made for computers. Our computers are F2, they are XORing all the time. And that's a big advantage over lattices. So lattices, they live in some larger field of Q, but then you have this arithmetic we don't like, it slows down, it causes problems. For hardware, this is really the thing that you want to go. And this was asking whether there are enough use cases for standardizing McAleese, and it seems so. So I probably will see it as a standard. Right? So it's very old, this scheme, and if you look at the literature, then sometimes it's also annoying because it's so old, right? And it's written in a strange style. You wouldn't write it like this today, and I found it quite of cumbersome when I first saw it. So this talk is really to introduce you to the system, so the codes are Gopher codes, we'll talk about that, and so on. And I will talk about also the bit security. So the best algorithms, and I will show you some algorithms, they require classically 2 to the 128 steps at least. So that means 128-bit security. And I will also show you that quantumly they require quite less, which is strange because it should be a post-quantum system, and we will also discuss why this is the case and why this is still fine for NIST. Yeah, and for the moment you should think of encrypting things like this. You take a message M, so that's a linear combination of the rows of this matrix, which is a public key, and this gives you a code word, you will see in a moment, and you disturb this code word arbitrarily with a number of ones, and the number of ones that we have for McAleese is, for this instance, 64. So that's not much. would have length 3,500 roughly, and we only have 64 errors. And well, if you want to decode, you have to extract this error. You have to find this error. We will see how this works. Yeah. Yeah, and by the way, I think this is a great summer school so far, but I had the impression that there was too few interaction with the audience so far, so I really strongly encourage you to ask questions, right? This really poses a lecture, and you don't understand something, it's very much fun. Okay, so let's do the basics. So we are, that's the object that we have, so we are treating the linear code, and throughout the lecture we are binary, so I omit this binary, always F2. So what is a linear code? It's simply a subspace of F2 to the n. So it's a vector space, and there's a lot of linear algebra here in this talk, you will see. So what again is a vector space? That's very easy, so it contains a zero vector, and if you have two vectors, then the sum is also yeah, and the difference as well, but the difference in F2 is sum. There's no minus in F2. That's also good. Well, and if it's a vector space, then it has a dimension. So K is the dimension of this code, and then you have a basis, which is called a generator basis in encoding theory. So it's a generator matrix, and then we can write this code as, oops, no, we don't want to erase it, as a row span of this matrix. So we multiply from the left by all possible vectors that we have in K, that's the dimension of the code, and you already see that the size of your code is 2 to the K. That's enormous. Huh? K was 2,700. So we can, this sort already create a message, right? So we can represent an enormous amount of vectors, 2 to the 700, compactly by 9 megabytes. Oh, it's kind of cool, right? This is what you want to have in crypto. You want to have a short representation of a large space. Okay, and here's the first example of a code. If you have never seen a code in your life, that's kind of the most simple that you can do. It's called a repetition code, R3. And what you do is, you have this matrix, general matrix, and if you multiply by a vector x, then you get x1 3 times, you get x2 3 times, and you get xk 3 times. Yeah? You're just expanding. Which means if you add an error, and you maybe have an error in the second position here, then you still have two good positions, and by a majority vote you would decode to the right. Right? Okay. Now it's a code, and it allows you some decoding. And I will sometimes speak about lattices because we have lattices tomorrow again. And in my impression, code-based and lattice-based, they are not really different things. They are just the same thing, right? If you go back here you have a generator matrix of some code. In lattices, you have a lattice. You would compute a lattice point, which is something like that. You would disturb it, and then you have some lattice problem. Right? It's almost the same by construction. It's not the same by the way we attack the schemes. These algorithms are different, but by the construction, they're very, very similar. And for lattices, you don't have to have decoding algorithms. That's kind of a big advantage also for lattices. They kind of come for free because you are working in a larger field, whereas in F2 you have to have really decoding algorithms. So here the decoding algorithm is very simple. You look at 3 of them and then you take the majority. There's 2 zeros and you decode to 0. Okay. That's decoding here. Okay, I have to warn you, there's a lot of definitions in this code-based world. I have to go through them. It's not really hard, but we have to define some language. Okay, so if you have an n-dimensional vector x, then, and this notion is very frequently used in this talk, the support of this x is the number of non-zero positions. Yeah? So those positions in the vector x that are non-zero over F2 non-zero means they are actually 1. Yeah? Okay, so the set of 1 position, so the support of this guy here is we number 1, 2, 3, 4, like mathematicians, not like scientists, so the support is really 2 and 3. These are the positions. Okay, so the Hamming weight of x is now defined as the number of 1 positions. So here as an example, if you have these, then you have 2 1 positions, so it's 2. The this weight. And the distance of two code words is the weight of their sum. Yeah? So if I do the sum of these two guys, then it's 1, 1, 1, 0, and then the distance, the weight of this is 3. So the distance of these is 3 because they differ in the first 3 positions. Okay, you see it's very elementary, right? Oh, by the way, so we had always breaks. Do you also want to have who wants to have a break after like 45 minutes? And who wants to continue with, who wants to live without a break? I encouraged you to have more interaction. Okay, good. So you'll see how tired you are after 45 minutes. Okay. So, so here's the distance of a code. So what I do is I look at all code words, and here in this example, these are 4 code words. And then I look among all distances between pairs of code words. So I take all pairs of code words, and I look among their distances, and then I pick the minimum. And you see in this picture, the minimum distance is here between these two, and then the having distance between them is the distance of your code. And that will be important for decoding, right? So the larger the distance, the more are they spread out in F2 to the n, and then the more unique is decoding. Yeah? Okay. So relative distance is always relative to the parameter n, and the dimension relative to n is called the rate of the code. Okay, there's lots of theorems in this talk and also lots of proofs, but the proofs are mainly for completeness. I don't go through the proofs, but I think they are helpful for you if you want to study, and then you have the proofs because I found it annoying. If you study the literatures and they say, oh, this is easy, and then I say, no, it's not so easy, I have to do it on my own now. Okay. Okay, so this is if you have a linear code, then the distance of this linear code is also the minimum weight of a code word. This is also very helpful, and we will do that throughout the talk. And then it's also easier to determine this because you have to go through all the code words only, not only the pairs. Okay, and here's the proof. This is not too hard. Okay. Let's go on. Let's go to Hamming boards. So, one notion, I'm sorry. A linear code is dimension k and distance dc is denoted as this 3-tuple n, k, and d. So, as an example for our repetition code, this stretches k dimension. That was our x vector. We multiplied by this matrix, and we get a 3 times k vector. And we already saw that the distance is 3. Why is that? We didn't see it. Well, we saw that the distance is a minimum non-zero code word. And if you go back to R3, then you can multiply by 1, 0, 2, 0, and then you get 1, 1, 1 here and all zeros here, which means that you have a minimum weight 3, right? So you cannot do smaller, so that's the distance of this code. Okay, fine. Now, one more definition. The Hamming ball with a center x, centered at x, and radius r is denoted by this. And it's the points which are at most r apart from your center. Yeah? And you should really visualize this. I'll do it in a minute. So you have a point in space, and then you pump up a ball of radius r. So here's an example as well. So if you have the center and you want to have a distance 1, then in distance 0, it's a point itself. And in the distance 1, you add a 1 in the first coordinate, and that's here, and you add a 1 in the second coordinate, in the third, in the fourth, and that's it. So the volume of this ball is, well, the point itself, and all 4 combinations where you add 1 arrow, so that's 5, and in general, well, that's this number here, right? It's a binomial coefficient because you can add I1 positions in distance I, n of I. Okay, you see it already has something to do with binomial coefficients, and we will treat them and we will show how to estimate them actually. I'll do that in a minute, and this is it. So we have to talk about entropy and binomials, so there's also a little bit of cryptanalysis, so we have to treat algorithms, and you might know this notation, right? So if you have a running time which is like this, then you usually write this kappa of n squared. So that means for polynomials we only take the largest degree, n squared, we don't care about the constant that is in front, and then it's lower and upper bounded by some function in n squared, constant function. So, and since we are treating very hard problems here, and most of them are actually NP hard, so the syndrome decoding problem that you already heard yesterday of and that we'll treat today, it only has exponential algorithms, and it's not a very much surprise because random codes is really NP hard. So that means that we have like exponential running times, and we also have maybe polynomials in our running times, but we gently ignore the polynomials. So this by this Tildel notation, right? So it doesn't only ignore constants, but also polynomial terms, and that gives us simpler terms. So let's use this notion. So the first fact is if you have n factorial, which appears in this binomial coefficients, then by the Stirling formula, this is n over e, that's the Euler number, to the n. So it's a little bit more than exponential. And you can write that kind of, I think it's kind of pleasant if you have this n over I that we had for the volume on the last slide, you can write it as a function of the entropy. See, it's I over n, entropy of I over n to the n, and usually that's for codes, that's kind of a constant here, and then you have an exponential function. Yeah, and the binary entropy function is defined like this here, and if you want to visualize it, it's like this. So it takes this maximum for 1/2, where it's 1, and then it takes this bell shape. And here's the proof for Stirling, but I think that's fine. Okay, so we have a way to treat these binomial coefficients. And there's more definitions, but hopefully we come to an end with the definitions at some point. So there's packing radius and a unique decoding. So what's a packing radius? Here again, we have a code. These are our code words. Again, we pump up our Hamming balls and we pump them up until they almost touch. Right? Just one thing before they touch. So that means, so we take the maximum of pumping around every code word, such that all these balls are disjoint, they don't touch. And it's easy to show that this called packing radius is just d minus 1/2. Why? Because in d12 they touch, so it's a d minus 1/2. And why is that important? Well, if I hit one of these points here in space, then there is a unique code word to which I can decode. That mustn't be efficient, right? But at least I have the chance that I have a unique code word to which I can decode, right? And usually in crypto we do like that. So we take a code word and then we actually do the maximum error. So we are really on the sphere here and we try to decode it, which is the hardest for decoding. Okay. So we get this promise that we have a unique solution. Well, and you like an example, then we have this repetition called 3 that had dimension 3, if I that had distance 3, I'm sorry, and then its packing radius is 1, which means I can decode one error, which we already did, right? So if we had one error here and this coordinate, we could do that, and if we have one error here, then we decode to this guy. Okay? So you're good so far? Not so far? Okay, good. Okay. So this is also important for crypto. It's called for crypto and also for decoding. It's called the Gilbert-Basharmov bound, and it relates the distance in a random code to its rate. So what it says is there exists an NK code, so I fix NK, and then the distance satisfies this inequality. So there is a large in a certain sense, there's a large distance. And here again, you see this entropy function that relates to the code. And, well, we ignore proofs throughout this talk. But important is this fact that I wrote down here. So codes with random generator matrix, they achieve this maximum distance. Yeah, so it's not really an inequality here, but you get an approximation here. So the entropy of d over n is roughly 1 over 1 minus the rate of this code. Okay, so we also use this Schubert-Vajanov bound at some point. Good. So what I want to do now is I go away from the generator matrix to the parity check matrix. So I go for the dual code, and I will gently introduce what duality means here, and so on. So this is again very basic, I hope for you. So an inner product in F to the n is defined as by this notion here. I use this bracket notion. I'm sorry for the quantum guys. So this is only inner products here. It's no tensoring or something like that. And this is just the sum. It's the xi, yi. Sometimes you write mod 2, but there's really no necessity because we are not going to have to. Right? So it's mod 2 during this talk. And well, you have these things here. It's symmetric. That's kind of clear. This we will use throughout this talk by the linearity. So you can stretch out sums in the first and in the second component. And if you have a scalar here, then you can put it out, or you can put it into the second coordinate. Okay, so two vectors are orthogonal if the inner product is 0, which is here. And maybe, also that's an exercise in the lecture, you have to show that for every vector, which is not the 0 vector, half of the other vectors are actually orthogonal. And it's a lot of orthogonality in F2, because if you do an inner product, you can have roughly 1 or 0. That's the only thing that you have. And it's easy to show that exactly half of them is 0. Okay. And the 0 is, of course, orthogonal to every vector here in F2 to the n. Okay. So, what's the orthogonal complement? So we start with a linear code, and then we look at all x's which are orthogonal to every code part. This is called the orthogonal complement, and I will do an example for you. So that's a generator matrix, and we want to really construct this orthogonal complement. So we look at all elements here that satisfy this. So they are actually orthogonal to the first basis vector, and they are orthogonal to the second basis vector. And then this is okay, because we have a basis, and we know if they are orthogonal to this, and they are also orthogonal to the sum. Linearity of this scalar product. Okay, so they have to satisfy these two equations, and I can spell out these equations, right? So this is actually, if I take the inner product now, I get the first component of x, the third component, and the fourth component. I write them down here, and here I get the first and fourth component. I have two equations, I can add them. If I add them, then these guys go away. So that means it gives me the restriction that x3 is 0. So the third coordinate is always 0 on all these vectors here. And then I have all combinations such that x1 and x4 are 0. And if I spell them out, then I end up with this set. And if you look at it a little bit, then you see, oh look, this is again a code, right? It's a vector space. It contains a 0, contains, well, it's generated by these two. Generated, because if I add these two, then I end up with this guy. Oh, this is magic. Oh, it's a code. This is, you see in the lecture, it's a question: is it always a linear code? And this is actually true, right? So if I go to the orthogonal complement, it's a code. It's called the dual code of this code. Right, this is 0 in here. So, and this is a notion for duality. That's a dual code. This is a linear code. It's a dual, and the proof is actually very easy. It constants 0 because 0 is a dual to every vector. And if you have two guys here that are orthogonal to all C, then their sum is also orthogonal, so it's also closed under addition. Okay, oh, that's perfect. So that means instead of the code itself, I can also look at the dual code. And well, there's some theorem. Well, if you have a subcode, then if you go to the dual, it kind of reverses, right? This thing, and I will show you something more on the next slide, how this behaves, the dimension of the code itself in the dual code. And you have one maybe last definition. So if you have a linear code, then any matrix P is called a parity check matrix if it satisfies this equation. So C can be expressed as all x in F2 to the n such that this equation holds. Parity check times x is 0. And in mathematics, you would say that's a kernel, right? And this is the explanation why you call it a kernel here. But this is also great for us because we can now represent the C either via its generator matrix or via its parity check matrix. And you might think, why did we all do this? This was an complement and so on. And you will see on the next slide. So actually in crypto it makes sense to take this guy, this parity check matrix. And the simple reason it's smaller than G. So we had this problem that G is super large and we don't want to have a large public keys, but P is way smaller, so why not take P? Yeah? And there's also more reasons for that, but I don't go into details here. Okay, so the theorem tells you if you have a generator matrix, that when you go to the dual code, then it actually is your parity check matrix here. So they change roles, right? In the dual, you get the parity check instead of the generator and vice versa. So you can switch between both of them. And I will show you in a minute how you actually do it computationally. Right? It's also very easy. So if you have the dual code, then its dimension is n minus the dimension of the code itself. So they add up to n. And this n minus k, I usually call the co-dimension of the code. No? It's the dimension of the dual. And if you do dual of dual, then you end up with the code itself. This is what you mainly expect. Everything fine so far? A lot of linear algebra, right? Maybe that's long ago for you, I don't know. Okay, but sometimes it's also useful for us as crypto guys to have some linear algebra background. Okay, so what are the implications for the Mac-Lease crypto system so far, right? So that was our generator matrix. It was our generator matrix. It was pretty large, but we already saw, okay, we can also use a parity check matrix. It's the same. And then, well, instead of the dimension of the code, I only have the co-dimension, which is like a force, which is great. So I can save a factor of 4 already in the public key. And then, again, this is a basis, so I can go to another basis. And maybe they are more compact bases. And what I do is I do a Gaussian elimination in this first square part, the 768 times 768. And then hopefully that has full rank, and I end up with an identity matrix here, and this is called the systematic form. And that's a compact basis because, well, there's an identity. I don't have to store it in my public key, so what I have to store in my public key is only this guy, right? And this is what you do in Mac-Lease. So this is really a Mac-Lease public key. And, well, we have public key encryption, so we have to have a secret key at some point. I will tell you in a minute what the secret key is, but it's a little more complicated to get the secret key, right? But this is what we do. And I said, well, let's do Gaussian elimination and let's hope it has full rank. And what you can show is actually it has full rank with a good probability. So this is kind of the probability that you have. Even for n going to infinity, you are above 1/4. And usually during this talk, I will ignore these rank issues. I will always assume that we have full rank. It's not really a problem, right? If you don't have full rank, then you can still do something. Okay. Yeah, so that's a public key. You're fine so far? Okay. Yeah, and this is a notion of an equivalent code. It's also very in fashion at the moment in crypto. So what is an equivalent code? If you have a basis, a generator matrix, then you call a code equivalent to see if there exists an invertible matrix, so that means a basis transformation of your code, and a permutation matrix P such that C prime is generated by this guy. So what you do is you redo a basis transformation, so probably think of S as being the Gaussian elimination, and you bring it into systematic form. And you are also allowed to permute the columns of your generator matrix, which means you are allowed to permute the entries of your vector. Right? Why is that? Because, well, if you permute the entries, it doesn't change your distance. It's just the same coordinates that you had before, just in other positions. And this is really also what you do in generating the public key for McAleese. We will see it in a minute. So you do a basis permutation, and you do a permutation of the columns, and then you end up with an equivalent code, which is your public key in McAleese, but the secret key allows you to do all the fancy decoding stuff, whereas the public key looks very random to you. So that's kind of the idea of this construction in McAleese. Okay, well, there's more exercises, but we can simply ignore them. Okay, and here's how you actually compute generator and parity check matrices. So if your C is generated by this generator matrix here, it's in systematic form already, then you go to the parity check matrix simply by taking this matrix A here, you transpose it, then it has the right dimensions, the right codimension, and you add an identity matrix of this form here, and then it's very easy to show that it's a parity check matrix. So especially if you multiply G by P, you get the zero matrix. And this is proving here in this proof, but I don't want to go into this details. Okay, so that's all very simple, all very linear algebra. So we can switch between generator and parity and work with both, but we prefer to work with the parity check matrix. Okay. So now we have to go to the messy details of a Gopper code, and this is usually if you attend a crypto talks and people say, look, this is a Gopper code, but this is too hard, so don't do it. So today we want to do it, and we want to find out that it's actually not so hard to define a Gopper code. We'll do it on the slide, and you will see it's very elegant, but then there's some messy details on the next slide. Okay, so here's McAleese parameters again. We recall n was this guy. And now I have two more parameters, but they are not really new. There's a t and there's a m. But the product of both is our codimension. Yeah? Think of the parity check matrix. That's the number of rows that we have in our parity check matrix. Okay, so this m, this 12, it defines a large field. It's not super large, but I call it a large field. It's a field with 2 to the 12 elements. So 2 to the 12, that's 4096 elements. Okay. And what we do now is we define a polynomial that's called the Gopper polynomial. It's irreducible, so it doesn't split over this large field. And this has degree t. Yeah? So I can write it in this form. It has coefficients g0 to gt, and all these coefficients are in the large field. Okay. And moreover, I have the following. I have Gopper points. So what I do is, out of this large field, recall I have 4096 elements in this field. I take n elements randomly and order them somehow. Right? And these are called alpha 1 up to alpha n. So I take 3488 out of this 4096 elements. Okay. And I will show you in a minute that actually this Gopper polynomial, together with these points, they define your secret key. So it's a very compact secret key as opposed to the non-compact public key, which is nice. Okay, and so here's already the definition of a Gopper code, and it's as simple as it can be, maybe. So what is a code word in this code? Well, it's a sum, and the sum is over f2 to the n, so the ci's are degree 0 and 1. And Forget about the zeros in the sum, just think of the ones. For those where you have a 1, no, Ci is 1, you have just the inverse of x minus alpha I modulo gx. Yeah? Okay. And if you look at this equation, when I looked first at it, I thought, so maybe there's an error, right? So this guy here, it lives in the large field. These guys, these inverses, they are also in the large field. It's x minus something. So if you compute this inverse, and it's usually a polynomial of degree t in the large field, but these guys, they are really 0, 1. They live in the small fields. It doesn't really make sense, right? How do I compute it actually? It's not a problem here, because it's a 0, 1 sum, so either they exist, these inverses, or not. It's still a mismatch, right? You're acting with two different fields, but it works. And it works because this is actually a subfield of the large field. Right? It's kind of the magic that also appears in this mechanistic crypto system. Right, so this is really fine. This is really nice for mathematicians, but it's not nice for computer scientists, because eventually we need a parity check matrix, right? We need this large matrix of zeros and ones that we want to compute, and that doesn't give us this parity check matrix, right? It's just well, some equations. But if you look at these equations, then actually if you spell them out, then here you have a polynomial, right? So this divides this guy, and then you can compare coefficients of these polynomials, and then it also gives you a parity check matrix. And this I will show you on the next slide, but I won't go through the details because they're a little bit messy. Okay. So, but what you should notice that this code is really defined by the Gopper polynomials itself, so the alpha i's, and this Gopper polynomial g. And this is, maybe that's also good, this exercise. Show that this is a subspace. I pretend, since I know the solution, that this is easy, but convince yourself it contains a 0 vector, because if I have zeros on these i's, and it's obviously 0 modulo gx, and also it's closed under addition, right? If I have two guys, which are 0 mod cx, I add them, both are divisible by gx, so the sum is also divisible by gx. So it's a subspace already, this we have proven already. So it's a code, but all that remains is to find a parity check matrix. Okay, so don't be afraid of the next slide. Okay, there's a lot of math on this slide, you see. Okay, so here I really spell out this thing, right? I use that this guy is a polynomial of degree t, and then basically I compare coefficients, right? So here are the coefficients of x to the t minus 1, blah, blah, blah. I spell them out. I write them in a matrix. I use this identity, blah, 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 blah. And then if I do everything properly, then magically I get a very structured and I think very nice secret key of a mechanistic crypto system, and there is this form. Yeah? So what happens? So the first row is just depends on alpha I and all. So I take alpha I to the 0, alpha I to the 1, up to alpha I to the t minus 1. This is already a little bit strange, right? It has a very local property. So I can very compactly write this, because I can write this first column only by storing alpha I, and it's the same for the second, and so on. And then I have a diagonal matrix here, and these are the evaluations of the alpha I again, so for the first column, and this is the inverse of this evaluation. Okay, so that basically means I have to divide this column here by g to the alpha I have to divide this column here, all the entries, by g to the alpha 2, and so on. Right. Still, if you look at it, this is not quite what we wanted, right? So we wanted to have a parity check matrix of dimension, codimension n minus k. Go back to here. So this is what we want, codimension n minus k. Now we have t. Now the number of rows is t. So we still live in the large field. So we have t rows that live in the large field. N is fine. Now this is what we wanted. But here we wanted actually n minus k as a codimension, because it's a check matrix. And this is equal to T times M. So we want to have a T times M here and a small field here. This is what we really want, because we want a generator matrix over the small field F2. And the way how you do it in Macaleese is here on the next slide. It's also very simple. So if you have a large field, yeah, then you can write it in the basis of the small field. Huh? You do this mapping here. You go from the large field to the small field, and you define F2 basis, and you spell it out as a polynomial, and you take the coefficient of this polynomial. Huh? So you take these coefficients, they are really 0, 1, and that's what you do. So if you think of your matrix, so for now it had T rows. For every entry, we write it in the F2 basis, so we kind of spread it out to M entries. So that means the T rows that we have are spread out to T M entries. And this is exactly what we want. So this is denoted here. So we start with a matrix that have T rows. For every entry, we spread it out such that we get T times M entries here. And this already destroys kind of the structure of this large field. It's kind of the magic, right? So once we do it, it's still a linear transformation so far, but it kind of destroys the structure, and we don't know how to go back. And then what we do to do the public key is just what we did before, right? We do a basis transformation, so we get the unit matrix here, we throw it away for the public key, and well, there's no permutation of the columns because we already did this permutation. So recall we chose the alpha i's in a random fashion, and that was already the permutation because the rows of this parity check matrix, they only depended on the alpha i's. So this permutation is there, but you don't see it in Macaleese because we did it initially for permuting the alpha i's. Okay, so that means your public key in Macaleese is really an equivalent basis of your secret key, and it's supposed to hide the secret key. And the transformation is as easy as it can be. It's just Gaussian elimination on the matrix. Let's say it's kind of cool. Good. So that's a Macaleese public key. And oh, I think we are doing very well in time. I'm way too fast. You have questions? Yes, hey!
Does the F polynomial need to be public?
Oh, yeah, okay. So, okay.
Right, the F that defines the big field, right? So
yeah, so what is public is actually, these are the public parameters. Yeah, I know the N, and I also see these things. I know the T, I know the large field. This I give out. I could also guess that. These are the secret keys. So G is secret, and the alpha I is a secret because they really define your parity check matrix. And what I also give out as a public key is then this transform thing. Right? So basically this. But there's no way back here. It's actually an open question how to do it most cleverly. I come back to this point if we study security of the screen. So what we really understand from Macaleese is the hardness of decoding in this Copper code, and this is how we analyze it. What I think what we don't really understand is the hardness of going back here. Right? I mean, an easy way of brute forcing things is we could guess the Copper polynomial, we could guess all the points, and then we have it. Right? But is there a smarter way using the information of the public key to go back here? I will discuss some things in the second part. Mm-hmm.
Yeah, so going back from the most right side to left side is hard, but going from the middle to the left, that's okay, right?
Yes.
Or, okay. Yeah.
Yes.
Okay.
So here everything is fine. Right? But also inverting the Gaussian elimination.
Yeah, no, so that's the problem.
Yeah. Yes.
The secret key is small, that's just small compared to the public key, right?
Well, yes, it's not small compared to how to say one discrete log, right? But still, it's surprisingly compact given that you have to store actually a large secret basis. Do you want to compute it for this? I mean, kind of the problem is that the n has to be so large in this crypto system, right? So what is the secret key? So you need t+1 coefficients for that. All coefficients have 12 bits, so it's 65 times 12 for storing G. And then you have to store all these points, so it's 3,488 times 12. I cannot do it, but
The assumption just said you can pseudo-randomly generate.
yeah, that's what you do. Exactly, that's what you do. And I will show you also in a minute that you can actually compress the secret key. Yeah? You'll see, if I give you parts of the secret key, then you can reconstruct everything, which means you can actually compress it, but we don't do it in practice. It's spelled out as an attack key, but it's also a compression of this key. Okay. Good. So, and now what I want to show you, I didn't do that so far, I want to show you that, I'm sorry. Oh yeah, more questions.
Going back to the question on F being secret. So like from the right matrix to the center matrix is like hardness of coding, and from center to left is because we don't know the description of the field, or
yeah.
something.
I think you are fascinated by this chain here and how to invert it. I mean, this is just nothing, right? I just spell it out in the small bases and that's it. And then kind of, when I do the systematic form, I do the Gaussian elimination, I kind of destroy everything that was there before.
Yeah.
Even if I wouldn't, we'll come back to this point, even if I wouldn't do that here, then Gaussian elimination is still a basis transformation that I cannot really invert. Right?
So like if I gave out the F and computed the Gaussian elimination over the big field, then it would still work.
It would still work, but it's not what we want. It's also not the definition of a binary code, right?
Yeah.
I think there is some confusion when people know the F is secret, right? In the room. But F is not secret. The description gives out.
You mean this small f here? Oh, this is of course not secret. No, you know actually.
Okay.
No. There's not so many choices actually for this f, and you could actually brute force it. So this is not hidden. This is actually clear. It's also specified in Maccabees. Oh, I didn't get that.
Okay.
Thanks for clarification. Yeah. So this is actually very clear. So there's actually nothing secret that's going on here. It's just a basis transformation. You go to a different basis. Yeah. And if I'm here, if you give me this guy, it's very easy to go to. This also. It's really the Gaussian elimination that destroys the structure of the code. Okay. More questions? They're in good shape now. Question time. Very good. Which is good because I don't have so many slides left for the first part. So please keep on going questions, or we have a large break, which is also maybe not a problem. Okay, so what I want to show you next is, we didn't talk of distance of this code for now, and I really want to show you that the distance of a Gopper code is at least 2t plus 1. You recall that t was the degree of your Gopper polynomial, and it's also, well, if the distance is 2t plus 1, then the packing radius is at most t, so I can actually decode up to 64 coordinates in this code. Right? And this is what we are going to show now, going to this distance of this code. Okay. Yeah, so here is what I call a Gopper syndrome. So what we do now is, you recall this definition of a Gopper code where we had ci's here, and then we computed over the x minus alpha i's. So if you compute the syndrome here for a code word, then we know that this guy here is 0 mod cheeks by the definition of the Gopper code. But of course you can do it for every point in space y, and then usually you get some polynomial here, which is not a zero polynomial, and that's called a syndrome of a point. So back again, the corollary, if you have a code word, you compute that, you end up with 0, that means your syndrome for the code words is actually the zero polynomial, right? And if and only if. So if it's not a code word, then it's not a zero polynomial. Okay, support you already know. It's a number of one positions. And what I don't like so much here is that I have these inverses in the large field. So I really want to erase these inverses. So what I do is I multiply by this guy, which cancels out all the inverses. This is what I do, and I call this the F polynomial. Okay, so let's do that. And now there's the following lemma. That's the derivative of this guy here, and if I take the derivative of this guy, then, well, for the ice term, the ice term x minus alpha I, is a polynomial of degree, that's the derivative is 1. And so I get the sum over all one positions of actually this product itself, where in the ith position I cancel out this term. Yeah? So this is really spelled out by this formula. If you take a derivative, then you take the derivative of the first position, so you cancel out the first position, you are left with the second, the two remaining, and you do it for all of these positions, right? That's what it is here. So it looks actually way more complicated than it is. Yeah, so this is actually a polynomial of degree support of this vector minus 1. That's the number of terms that I have here. Okay, why do I do all that? Well, I want to show that actually you have a code word if this polynomial here, the derivative of this f polynomial is 0. You go back, we showed already. This is a code word if this guy here is 0, and that's equivalent to showing that this guy here is 0. Right? And basically I told you I take this guy for cancelling out these guys. So what I do is I basically multiply this s by this guy, so I cancel out all these guys and I end up with the derivative. That's what I do here. And this is what the proof actually does. I don't want to spell it out. The proof really multiplies this guy by this guy, and then you see it's actually this derivative, and that shows you, well, this is 0, yeah? If this is 0, then this is 0, and vice versa. Okay, so that's an easy way actually to show that you have a code word, so you just compute this guy and check whether this is 0 in this code. Okay, so this more technical lemma, I don't want to get into the proof here, but you can actually show, and that's a F2 thing, so if you have your code with your Gopper polynomial, then you can also take the square of your Gopper polynomial, and this is still fine. Because F2 magic, right? So go through the details, the proof you will find here, but you can actually do this g squared. And that gives us a distance. Okay. So here's the theorem for the distance. Here you have a code. Your Gopper polynomial has degree t, and we want to show that the distance is at least 2t plus 1, so we can decode up to t points in this code. And the second part, we will also look how to decode actually. Okay, so how do we prove it? So we really do a proof now. We take a code word of minimal weight. So the weight is the distance of this code word. Now we compute this derivative here. And since it's a code word, we know that it's 0 modulo gx. But we also proved in the last lemma that this is also 0 modulo g squared of x. Okay, what does that mean? So this guy here has, g has degree t, so g squared has degree 2t. And, well, this is a multiple of gx, so it must have at least degree 2t. It's a non-trivial multiple of it. And then, well, this guy divides this guy, so this degree is is larger than this. This is spelled out here. And you can also see that the degree of this guy is actually dc minus 1. Why is that? Because, well, the support of this, so the degree of this polynomial is basically, no, this is only a sum. So here you see the degree. It's the support of this guy, well, minus 1, because we cancel out one coordinate all the time. So the degree of all these polynomials is actually dc minus 1, right? And then you get the formula. So dc minus 1 is larger than 2t. So our Gopper polynomial has at least degree 2t plus 1. So it's t around decoding. Okay, so that's a lot of messy stuff. And then we already go to the second part, to the destructions. And I think we deserve a larger break, which is maybe also fine. Unless you have questions, of course. Some questions from your side. No, you are happy. You want to break. You have a question?
Yes, everything that you showed also could work with hypercodes, right? You can also do the...
It could work, but history also tells us that if we change the code, then it's in a very unstable situation. So people tried it with Sweet Solomon code, it was broken, they tried it with other codes, it was broken. It's also a subtle thing, right? We saw that there's structure, there's a lot of structure in the secretary actually, right? It's a very structured matrix. And it's not, at least to me, it's not so clear why Gopper codes are so cool, whereas others are not. Yeah? No questions? Okay, you deserve your break. And then we go back at, you know, fine. Do we have coffee? Annie is speaking.
I think the coffee will only be there after class, probably. I think so coffee is a dessert.
Okay. Shall I continue with some stuff and do 10:15 or so? Maybe that's good. Yeah, if we don't have coffee, then it doesn't make sense. That's true. Okay. Okay. Then we have a shorter second part. That's also fine. Okay, good. No. Then let's go on.
Can I ask a more basic question?
Yes.
So the way I understood it is you have from a coding perspective, you have a encoding technique for which you only need to know that binary P.
Yes.
But for decoding, you need to know G and alpha information.
Exactly. I didn't talk about decoding and how. I mean, we have to come to a point where we actually decode at some point. Yeah. I will show you on these slides. So we really need the decoding capability for going from the ciphertext back to the message.
But what I don't get is that if you know matrix P, isn't that enough for decoding of a linear block code? Is Gopper code is it linear block code or it isn't?
It's a linear block code, yeah.
And isn't that enough to know P for that purpose?
You can decode, but it's a hard problem. If you just have P. If you just have the public key, then it's a really hard problem. Whereas if you know all these alpha I and the Gopper polynomial, then you have an efficient algorithm for doing the task.
But isn't it just about finding the dual matrix? Or
No, it's not. No, decoding is not finding the dual matrix. I didn't properly define what decoding actually means. So, in a certain sense, well, maybe I should do this, and then we repeat the question again, and then we see whether it's clear or not.
I have a question.
Yeah.
Regarding the degree argument
Yeah.
a few slides earlier.
Yeah.
So we take the sum of these products
Yes.
over the support.
Yes.
So the highest term of that is the x to the weight minus 1,
Yes.
and then summed up over the support. So do we know that the support has an odd amount of elements so that these don't cancel out, these high terms?
Oh, yeah, it's at most. Yeah, you're right.
I mean, unless we know that this code word is already of odd weight, so it has an odd number of supported points.
We could. There's a lot of cancellation SF2, right?
Yeah,
Not
that's
forget to
mentioning another amount, right? So
Yeah.
it's actually-
Does it destroy the argument? Decree, so the decree could be actually less here, right?
Yeah. Wait. Yeah, exactly. But then,
And that's a problem for the proof, isn't it?
yeah, there's some step that still needs to be argued, I guess, that the weight is odd,
Yeah.
if that's not true.
Nice. Not clear to me that the weight is odd. Why should it be? No.
I don't know, maybe due to some structural
Oh.
thing of the code, but I don't
Does
see
it go into the wrong direction? So is it? But still, FC is a non-trivial multiple of G of X, right? Problem actually? I think it's fine, no?
It's just, I guess the degree could be smaller, but it should. Yeah, it should be fine, I think. As long as FC. As long
Yeah,
as
it's not zero. It's not a trivial polynomial, right? It's a non-trivial concept. So this is really a non-trivial polynomial. It's not a zero polynomial.
and plus into cancel out.
Yeah.
I think it's still fine.
Yeah, it's still fine.
Yeah.
It's just not equal.
Yeah, it's just not equal, so yeah, exactly.
I have a maybe related question. If you can go from G to G squared, I guess you can also go from G squared to
No.
G to the 4.
No. Actually, I tried it.
Okay,
It would be
because
cool
then-
and it would break something. No.
Okay.
That's really the end. So look at this proof here before, and then you see why it goes for. You use F2 once, but you cannot use it twice. Yeah, I also tried that. That's very tempting, right? Basically, what you're also using is that this holds here F2. But then it's the end of the story. Okay, good. Yeah. You're also trying already a cryptanalysis, that's very good. So welcome to the cryptanalysis part of this talk. But let's wrap up first what we did for Macaleese. So we have a public key, which is this public parity check matrix. And we have the secret key, which is these Gopper points, alpha 1 to alpha n, and our Gopper polynomial. So what we do now in Macaleese is we have a message m, and we embed it injectively, such that we can invert this embedding into a vector in F2 to the n with weight t. It's not hard to do, but it's also not super easy to see now, so you don't have to see it by now, but if you're interested, I can show you how to do. Okay, so here's a simple binary vector, and well, we embed it such that we have an arrow vector which has length n and weight 64 in our case. And now the encryption is the following. We multiply our parity check matrix by this arrow vector, and this is called a syndrome. And now you come to this famous syndrome decoding problem that Annie spoke of yesterday. So the syndrome has length t times n, so it's the codimension of your code. And well, this is an arrow vector, and if you are capable of decoding in your code, then you can retrieve the arrow vector if you are within the packing radius of your code. So what you do is you use the decoding algorithm, and we have to do it in a minute. So we recover the E from the syndrome S using our secret keys L and G. And here we really have to use L and G, right? So we don't use P, we use it as a secret key. And then we go back to E, and then we invert our embedding, so we go back from E to M because it's an injective thing, and so we recover our message. So speaking in security notions, you heard yesterday from Katrin, this is only public key encryption, it's also deterministic, so it doesn't fulfill any good security notions, but then you have these transforms like FO and so on, and then you can get key encapsulation of that. So this is fine, so as long as this is actually secure and we cannot do this, and so we cannot actually decode in such a linear code for parity check matrix P, which is our public key. So that's a syndrome decoding problem. I give you the public key, parity check matrix. I give you you the syndrome, which is the encryption of a message, and I give you the weight. And I ask you to find the error vector of a certain weight, omega, such that it fulfills this parity check equation. So the syndrome is P times E. So this is really the syndrome decoding problem that you already saw yesterday. Okay, so what does that mean? It means you get a parity check matrix here, codimension n minus k, and columns, and you have to find a sum of the columns of this parity check matrix such that this sums to S. Right? And this is really the problem that you face as an attacker on this scheme. Right? So you only get this public key here. You don't know the structure that was hidden by our transformation, going from the secret key to the public key. And now you are really left with decoding in a hopefully random linear code. And this is supposed to be hard if you don't know this information. LNG, and there's a lot of time spent now in the second part of the talk to explain why this is hard, what are the best algorithms for doing so, and so on. But I will also show you that once you have this trapped or LNG, then it's actually easy to get all the coordinates of it. Yeah? But does it answer your question also? No, it doesn't. So what is that?
No, I'm just, I have to remember. I mean, my impression was once we have the syndrome matrix, then there is always some table or something that tells us what the error is. But I'm assuming that doesn't.
Oh no, you cannot enumerate it. I mean, this is all huge, right?
Okay.
I mean, the dimension is 3,488 over 64. That's a lot of things that you cannot enumerate. Yeah, we're doing something smarter than that, than just enumerating. We will come to this point. Okay. Oh, I still have to fill some minutes. Okay. Okay. So let's do let's think about this problem for a while, right? So why should it be actually hard, this problem? So one thing is, I just give you too few linear equations. Yeah? If I gave you n linear equations, then it would be a quadratic system. It's linear. I just would solve for E. You know that there's a unique E, there's a unique solution, so just do it by Gaussian elimination. That's it. Well, now it's underdefined. That means I have a lot of solutions, and only one of these solutions, E here, actually has small weight. It's kind of hard to find among all these solutions the one that has small weight. That's kind of the thing. And we'll see also in a minute on the next slide that it's very easy to get some solutions here. Right? So for instance, it's very easy for me to get to solutions E which have weight n minus k half. Yeah, but n minus k half is way larger than omega. N minus k half, n minus k was 760 something, so n minus k half is roughly almost 400, but I really have to find solutions which have weight 64. So I really have to find 64 columns that sum to S. Super easy, right? It's a problem. It's very hard. It's very combinatorial, and also the algorithms that we have are very combinatorial. But still you see, well, if it would be square, then I have Gaussian elimination. And that's kind of the key thing that people use for the algorithms. So here's the most famous algorithm. It's called Abranges algorithm from 62. Actually very easy. It's called information set decoding, and you will see in a minute why. So you have this matrix. Well, this is not square, but still I can do Gaussian elimination on the first square part. And again, ignore that it might not have full rank and stuff, but this is all fine, right? So what I do is I really do Gaussian elimination, then I end up with a unit matrix here, and the Gaussian elimination matrix is this basis transformation, so I have to multiply it in here, and I have to multiply it also for the syndrome. And kind of mentally, I already split my error vector, right? I split it in the first codimension and the remaining part, E2. Okay, and just by this picture here, we get this equation here. So what do we get? We get E1 times unit matrix, that's E1 itself, get E2 times this matrix here, that's this matrix here, and well, that's the transform centrum. So now assume for a moment that E2 is actually 0. So what happens then? Then you have that E1 is actually this guy here. And this gives you a way to check whether this actually happened for E2. Yeah? If E2 happened to be 0, then you already see E1, and then you know that E1 must have small weight. Then you know that the weight is 64. So what you do is you compute this guy here on the left-hand side, and you check whether it has weight 64, and once it has 64, you know that E2 had to be 0. Right? That's it. And what you also see from this equation here, it's very easy to construct solutions, namely solutions with having E2 equal to 0. I just set this to 0, then this guy cancels, then I get some E1, which might not have weight 64, but it has at most weight the codimension. That's what you get. Right? So it's very easy to get some solutions of the system, but the one small solution is not so easy. But it's already in this algorithm here. I mean, what we have done so far is we have seen that for this parity check matrix, we could also permute the columns of this guy. Right? So if I permute the columns of this guy, then I go to some equivalent code, which means if I exchange two columns here, then I also exchange the positions here. So then the idea of the algorithm is the following. I exchange the positions here between these guys such that all of the ones that I have here, all of the 64 ones, they all end up in the E1 part, and this is all 0. If this happens, then I'm back to Gaussian elimination. I do what I did here. I check whether this is really true. I check whether the weight of this guy is 64 after the permutation. If not, then I repeat this, and this is already the whole algorithm. And in a certain sense, it's almost kind of the best algorithm that we have for the information set decoding for MAC-Alice parameters in the sense. I will go to other algorithms that give you a little bit of an advantage, but it's very important that you understand this algorithm. It's actually super easy. And I will spell out this algorithm again now in more algorithmic form. Yeah? And the idea is really we permute until we end up with all the ones in the first NK columns, and these NK columns are called an information set, and this is why these algorithms are called information set decoding algorithms. Okay, so here's the algorithm again, form of really an algorithm. So I start with a parity check matrix, I start with a syndrome, I know the weight, and then I repeat the following. I repeat to choose random permutations of my matrix. So I permute the columns. I end up with a matrix P1, P2. I do Gaussian elimination on this P1. Well, I do it only if it's invertible, but we ignore. And then we saw that this is the equation that we have to check. This is a transform syndrome. I check whether this weight is actually our 64. And if this is the case, then I know that I have a solution, because I can read off the E1 already, or maybe I didn't show you that. So if this guy here is 0, then I can really read off the E1, because the E1 are just the one positions of this. Right? That's it. So I can read off the E1, and I know that E0 is 0. Okay. So this is the E1. This is E1, this is 0. And then I have to revert my permutation, of course, right? Because I permute the colors. That's our algorithm, very simple. And what you also should observe is that this Gaussian elimination, we don't really count because it has polynomial complexity. And I told you, well, since I have a mixture of exponential complexity and polynomial, I don't count this polynomial complexity. But it also has a low success probability. So we have to permute 64 ones into the first 700 something positions So what's the success probability? So this is our 64. We have to permute it in the information set. That's of that size. And this is the total number of possibilities that we have. Okay, so how long do we have to run this first loop then? Well, until we are successful in doing that. That's the inverse of this guy. So it's a geometric distribution. So I flip this. So that's basically the running time, and then this tilde O comes from the Gaussian animation. Okay, so you can plug in the McAleese parameters here, and then you end up with this guy here. So that means your complexity is kind of okay, right? So we were heading for 128-bit, and we get 143-bit for this algorithm, which is not the best. But it's also a cool algorithm in a certain sense. It's very easy to implement, very easy to parallelize. So I can very easily parallelize this first step here and run different permutation on all my parallel instantiations. It's also cool because it has low memory. Right? I don't have to store anything, just matrix to Gaussian elimination. It's also very cool, this algorithm, because it admits a very simple quantum algorithm. This is a quantum school, so we should also talk about some quantum stuff here. And that's a surprisingly simple algorithm, which is basically Grover search. I think you heard a lot of Grover search already. And there's a slight generalization of Grover search that's called amplitude amplification, which is basically Grover search itself, but it's kind of more useful. So what it says is the following. If you have an algorithm with a small success probability, which we had in our algorithm, right? So we had a small success probability per iteration of Brandis algorithm. Then we concluded classically, if we have success probability p, then we expect to have 1 over p instantiations of this algorithm until we have success, because that's the expectation of your geometric distribution, right? That's what you do classically. Well, quantumly, you can show you don't need this 1 over p, but by some Grover steps, you get a square root. It's a typical quantum speed up. So whenever you have an algorithm with this probability, you only need square root of 1 over p iterations of your algorithm until you have success. Now, this is without proof, but it's basically Grover's algorithm. So what does it mean now for the McAleese crypto system? It's a little bit strange, this conclusion, right? So in McAleese, we had this probability p here that our permutation was good. So classically, we concluded that we get this 1 over p. Quantumly, we get the square root of this, which is actually quite small. So it's only 72-bit. So that means if you take a quantum part, quantum version of your prior algorithm, then quantumly it only gives you 72 bits security, which is actually below what you want for NIST, right? Because NIST says for the small categories, we need 128 bits, but not only classically, but also quantumly, right? And we have to, no, well, I will discuss it, right? And that's a way out, right? Okay. So now people said, look, well, this is Grover's algorithm, it has a large depth, right? Because you have to do this iteration, this Grover iteration over certain things. And then they said, well, look, we are fine if there's a Grover algorithm that does a job and does a cryptanalysis and has maximal complexity like 70, 80-bit, because we assume that you cannot do it quantumly, right? And this is actually a difference if you compare to lattice schemes, right? Here you have this Grover version, you also have it for lattice, there are also Grover versions, but they are not as effective as this. And this is basically because you have a very simple algorithm here. Yeah? The simpler your algorithm, the more speed ups you get quantumly, the more advanced your algorithm. I will come to more advanced algorithms classically in a minute after the break. But then your quantum speed ups are not that dramatic, right? And obviously, I mean, by definition of NIST, it's tolerated that you have this algorithm here because people assume, well, if it's only Grover, not some Schwarz algorithm where you have a large depth in Grover, then we don't expect that quantum algorithms can solve that. And well, I think this is actually a drawback, right? If you really believe in quantum computers and in quantum security, then well, you have this freedom. It's kind of unavoidable. Yeah? You disagree, I mean?
Yes.
Yeah. Fine.
Because you cannot parallelize ROBO. So ROBO really is terrible to parallelize. That's point one. And if you actually want that speed up, you have to run the full depth circuit.
You have to do it, yes.
I mean, the reason that we use such large numbers is not because we assume one can do 2 to the 80 computations sequentially, but because you can easily do them in parallel.
That's true. That's what we also do if we do cryptanalysis, right? I will show you some experiments which are highly parallel. That's all true what you're saying. But I mean, kind of the measure that we have for cryptanalysis is the running time, right? And that translates 1-to-1 in the depth of a circuit, of a quantum circuit. It's a natural measure.
No, it's the depth of the circuit that you actually need to obtain a result. And you can reduce the depth by parallelism, which doesn't work for Grover. I mean, you can do this with Grover, but it would actually explode your width.
Yeah, I think there are trade-offs that you can do now. So if you limit your depth, so there's a bound that this gives, so what is the depth to 60 or something, and then you can kind of do that, but then you maybe go beyond the 128 again, right? It's kind of the way out. It's a little bit shaky, right?
No, I mean, the good thing about Grover is you can prove that you cannot do better
Than
this
parallelism. That's true.
Parallelism is really bounded. Like you cannot get anything better. There will not be a new algorithm that actually does this more.
Yeah, so this is an upper bound for Grover. Okay, fine. I cannot prove that. That would be dramatic, right?
That parallelism cannot, that there will not be a smarter way to parallelize.
Yeah, that's also true. Yeah, but still, I mean, this is pretty far away from what you want, right?
And due to the 72.
Yeah. I don't care too much because I don't believe too much in quantum algorithms. So. It's also a little bit strange, right? It was kind of the initial goal of us to have it really quantum secure, and you have this speed up here, right? You can discuss about quantum this, so I think this is already a lot of things. We will discuss also some things. I mean, we only look for running time here. We don't consider memory. This is good here for Prange because it's very memory efficient. I will come up with other algorithms which are less memory efficient in a minute. They are a little bit better in time. And then the question is, what is the cost of memory? That's also a lot of debate if you follow this. And if you have problems with sleeping, then I can recommend follow the list of lists and read some discussions, and then you sleep very well. Okay, so maybe that's a good point for right now. Okay,